PCG with their levels, length of stay, pay delay. Logistic regression model. We know that multiple linear regression model can be used for predicting a continuous dependent variable, but to predict a categorical variable, same method cannot be applied. To predict categorical variables through the use of probability of belonging to each class. In the first step, the estimate of probability of belonging to class 1 is obtained. In the second step, a cutoff value is used on these probabilities. And P is the probability of belonging to class 1. 1 minus P is probability of belonging to class 0. And odds ratio is P by 1 minus P. Log of odds is called logit. And these are the results of logistic regression model. This slide shows the different columns, estimate, standard error, z-value, and p-values for the different variables. Before we look at one more result of logistic regression, in this slide we'll learn about what is deviance residuals, chi-square, and maximum log likelihood. Deviance residuals is a measure of model fit. Chi-square determines whether a variable is a significant predictor or not. How choosing parameters of a logistic curve influences the maximum likelihood to fit a logistic regression model. And these are the results of analysis of deviance table, the second result of logistic regression with degrees of freedom, deviance, residual, degrees of freedom, residual deviance, and the p-values. These are the plots of logistic regression model. The first one is residual versus fitted, normal QQ, scale location, and residual versus leverage. Now let's look at the different definitions behind all these plots. Residuals are obtained by the difference between predicted and observed responses. It's a form of error unexplained by the fitted model. Regarding QQ plot, its residuals, it checks actually if residuals are normally distributed or not. Looking at residuals, we can say if a model is appropriate. This is about ROC, which is called receiver operating characteristic. It's a measure to evaluate models. It's a graphical plot of true positive rate versus false positive rate. Greater ROC area, better is the model. This shows the ROC plot for training, validation, and test data for logistic regression model. Purple curve is the logistic regression model, and the blue line is the baseline model. Various ROC values for training, validation, and test data are shown. If I have to explain what is training data, then it's the data from which classification or prediction algorithm learns. Once this algorithm is learned, it is applied to another sample of data, which is called validation data, where outcome is known. And the third one that we saw was the test data to use with the model finally selected to predict how well it will do.
Okay, looking at the ROC plot for the logistic regression model, we see that the ROC plot for the training data set, the validation data set, and the test data set are very close to each other, which tells us that it's a good model, and then there is no large variation between these values. So moving ahead now, we'll take a look at the neural network model. So one of the successful applications in data mining is the neural network model. It is a multi-layer feed-forward network. The idea is to combine input information and capture relationships among and between the variables. The network learns the relationship from the data. There is an input layer consisting of nodes which accepts input values. Successive layers get input from previous layers. The last layer here is the output layer, and the layer between the input and the output layer are called as hidden layers. Now we look at the summary of the neural network model, in which we have some variables, and to define these variables we have B as the bias associated with a node. H1 represents the hidden layer, node 1. I1 represents the input node 1, which is nothing but the input variable one, and O represents the output node. Now let's look at the ROC curves for the neural network model. Okay, so looking at the ROC plot for the neural network model, here again we see that the training data set, validation data set, and test data set have very close ROC values. And also if we see the ROC value or ROC curve for the full data set, it's very similar to what we have above. So we can say here that the model is accurate, and also if we had huge variation between these values, we would have reconsidered or remodeled again by excluding certain variables. So now we'll move on to the random forest model.
A random forest is an ensemble of unprinted decision trees. Ensemble models are often reversed of variance and bias. Random forests are often used when we have large training datasets and particularly a very large number of input variables. The algorithm is efficient with respect to a large number of variables since it repeated subsets the variables available. A random forest model is typically made up of tens or hundreds of decision trees. It is an extension to classification tree. The multiple classification trees are created from the data and combine their output to get a better classifier for prediction, which then use different trees called forest. This is summary of our random forest model. Type of random forest is classification. We set number of trees are 200 and the number of variables tried at each split is 7. The out-of-bag OOB error estimate is 17.18%, which is higher. That means this is not unbiased in many tests. The table shows the two different measures of variable importance. The first importance is the scaled average of the prediction accuracy of each variable, and the second is a total decrease in nodes. In practice, splitting on the variable over all trees using the Gini index, the higher the value, the more important the variable. And the ROC curve is 0.932 for the training data, which indicates building a random forest and evaluating it on training dataset gives a perfect result. It would tend to tell us that our model has overfitted the training data. Applying the model to a test dataset indicates that it doesn't generalize quite well based on the area, and the ROC curve is 0.68 for the test data, and that it does suffer from the usual consequence of the model that has overfitted the training dataset. One of the classic machine learning techniques widely deployed in data mining is decision tree induction, Quinlan 1986. Using a simple algorithm and a simple tree structure to represent the model, the approach has proven to be very effective. This slide shows a summary of the conditional tree model for classification. Conditional inference tree have 41 terminal nodes. Response variable is days in hospital Y2. Number of observations is 54,102 for training data. This displays a decision tree. Area and the ROC curve is 0.66 for the training data, which indicates building a decision tree model and evaluating it on training dataset gives a good result. Applying the model to a test dataset and validation dataset indicates that the area and the ROC curve are very close to the training dataset. This means that decision tree model is good but not excellent. Lift is a measure of the effectiveness of the predictive model calculated as a ratio between the results obtained with and without the predictive model. Cumulative gains and the lift chart are visual aids for measuring model performance. Both charts consist of the lift curve and a baseline. The greater the area between the lift curve and the baseline, the better the model. This shows the comparison plots of 4 models for training, validation, and test data. Comparing the plots, area and the lift chart are closer for all the models except the random forest model. We can understand that the neural network model lift chart is bad because random forest model overfit the training dataset. The means we cannot use the model to predict new observations. This shows the lift chart for 4 datasets of all 4 models. The neural network model is bad, though the area and the lift chart of the first model is high but overfitting training dataset, which leads to that we cannot use this model to predict new observations. This shows the comparison plots of the 4 models for training, validation, and testing dataset. Comparing the 3 plots, average and the ROC curve are closer for all the models except the random forest model. We can understand that the neural network model ROC curve is bad because random forest model overfits the training data. The means we cannot use this model to predict new observations, though the ROC value is higher. This shows the ROC curve for 4 datasets of all 4 models. The neural network model is bad, though the area and the ROC curve of first model is highest but overfitting training dataset, which results in that we cannot use the model to predict new observations. A perfect model performance assisted through a risk chart is then a risk chart that maximizes the area and the 2 curves. This shows the full risk chart. The performance of the neural network model is bad, except the first model, which is unable to be used because it overfit training dataset. Conclusion 1. Neural network model is the best model by criterion of ability of prediction. However, in general, there are lower ability of prediction for 3 models. 2. Because the ability of prediction of neural network model is very close to that of logistic model and tree model, we also can see logistic model and tree model are good on new observations. 3. If we want to know some difference between levels in character variables on target variable, logistic model is the best. 4. The decision tree model is the easiest for classification. 5. Because random forest model overfit training data, we cannot use it to predict a new dataset. Thanks to Dr. Xijin Ge for your continued support during the whole semester in learning different skills in data mining. I would also like to thank all our group members. Thank you for watching the video.